welcome to the 15th lecture. Today we will start with the rigid body dynamics. Already we have covered the rotation and rotational kinematics in details, except few things which I have left for the discussion in tutorial, or either I will upload as the supplementary material for your help. So, today we are going to discuss about the rigid body dynamics, but for that what we need the basics of the Newton's law, that must be very clear. Okay. So, let us start with the Newton's law. Popularly we have three laws, and the books they credit Newton's for all the three laws, but the reality is that only the third law is due to the Newton, it is a contribution, and other two laws, the first and the second laws, were already existing. Okay. And to that Newton added the third one. So, we discuss the basic things of the Newton's law. The first law states that a particle remains in its state of motion or rest until unless acted on by an external agency or external force. And quite often this is also called the law of inertia. So, we will discuss the fine points of all these laws. The second one, it states that the rate of change of linear momentum proportional to the force applied and takes place in the direction of the force. And the third one, it states that action and reaction are equal in magnitude and opposite to each other. Opposite in direction and takes place on the two interacting bodies, which are two different bodies on the So, this law is credited to Newton. Okay. The other two, these were existing before him, but as of that all the three laws they are accredited to him. So, now we take the second law first. The second law is to state that the rate of change of momentum is directly proportional to linear momentum is directly proportional to the force impressed. Okay. And or otherwise we can write. So, F will be equal to k times dp by dt, and by definition this our p, the linear momentum, this is the linear momentum. By definition, this is m times v, where m is the mass of the body. So, here the assumption is that mass of the particle is constant. So, Newton's law is applicable to a particle, and it so happens that then it is extended to the different bodies. Now, if you look into this equation, so this can be reduced to k times d by dt m v, because m is constant. So, this can be written as dv by dt. Okay. In SI system, it is taken so that k turns out to be SI system, k turns out to be 1. Okay. So, how it is done that if on the left hand side it is chosen as 1 Newton. Okay. So, on the right hand side, so 1 Newton is defined as the force which produces an acceleration of 1 meter per second square in a body of mass 1 kg. So, we can see that if the body mass is 1 kg and dv by dt, this is the acceleration. So, k m times a. So, this is 1. Okay. So, that gives you, here we have written magnitude wise, the vector notation we are not putting. So, this is k. So, k turns out to be 1. So, the SI system, the things of the units are defined such that k equal to 1, and therefore, your Newton's equation often you find in this form. Okay. Now, earlier also I have stated that if f equal to 0 means that there is no external force, If f equal to 0, so what will be the situation? So, this simulates f equal to 0, simulates the, or say f equal to 0, it also states otherwise, that in the first law, if you see that if until unless acted on by an external force. So, if f equal to 0 means there is no force acting on the system. So, either the system will be in the state of rest or in the motion, which is visible from this place. So, f equal to 0, this implies, and this implies a equal to 0 and v equal to a constant. So, therefore, if v is a constant, so it can be either equal to 0 or it can be either equal to say some parameter v. Okay. So, both are possible, that either it is moving with constant velocity or either it is at rest. So, in other words, Newton's second law states the first law. Okay. This is what it implies, but then the question arises that what is the need of the first law then? Okay. So, the question is then why the first law is required? Okay. See, the thing is that the first law defines the inertial system. In framework of which the second law is defined. Without an inertial system, your second law is not valid. Okay. Just for take for example, this is a disk which is rotating with angular velocity omega, and a particle is placed on at a distance of r from here. Okay. So, this will also be rotating, but as you know that if there is no friction available, enough friction is not there. So, this will slide out. Okay. So, this will not stay on the board. So, if you see that in this system there is no force acting, this is a rotating frame. Okay. This is a rotating frame which is a non-inertial frame. A rotating one. So, this is a non-inertial reference frame. So, if your particle is here, so it will slide out, means apparently you are not applying any force, there is no external force acting on this particle, but still the motion is present. Okay. And if you consider the same thing in this system, in this rotating system, if you apply the second law, then you will be in error. Okay. Because the second law is not valid in the for the non-inertial system. Okay. For that you need an inertial reference frame, only then you can apply. So, the first law, it defines the inertial reference frame, and together with also it states something that there is something like the inertia existing in the system, which does not allow the system to change its state. It may be particle, it may be a body or whatever. Okay. So, a particle is there. So, if it is moving, it will keep moving. If a rigid body is there, so it will keep moving. If or either even a rigid body is moving, so it will keep moving until unless acted on by certain force. It may be friction force or any sort of force. So, the first law, it defines both the inertia and it sets the framework for the second law. So, this setting the framework for the second law, this is not mentioned quite often in most of the textbook, but it is a fact that it is used for setting the framework for the second law. And also together with this also gives the notion of inertia. Okay. And the third law, which is very obvious, if we have two bodies, okay, just like the two masses colliding together. So, this will apply force on this here in this direction, and this will apply force here in this direction, and these forces will be equal and opposite to each other. Okay. So, within this framework, then we start working with the equation of motion. So, in a frame, if we have a rigid body, say here, okay, and this is a mass of the rigid body, which we can say this is delta m I, and its velocity is here in this direction v, and let us say this is the position vector of this point, which will indicate by r I. Okay. So, now if we apply the Newton's law to this particular point, so we can write, after the whole reduction we have written, F equal to k is equal to 1. So, this is dp by dt. So, we will write here df or delta f, we will write this as the delta f, and this p, instead of writing here p, we can write for this particle as delta p I. Okay. So, this is the linear momentum of the particle delta m I, and which is nothing but delta m I times v I. Now, if we sum over all the particles, so this is delta f I, and this differential operator and the summation operator is a linear operator, we can exchange it and we can write this as delta m I and this is nothing but your delta p I, means this we can write as dp by dt, where summation delta p I it extends over the whole body, which we are writing as the p. This is the linear momentum of the okay. So, this particular equation we can play with this little bit more. So, we have delta f I, you can put here f, and this we can write as d r I by dt. We know that V I, the velocity of the particle I, this is the ith particle here, which we have shown. Okay, so, this particular equation we can also write it in this way, and because the mass is constant, mass is not a variable, and therefore, we can take out this d by dt outside, and this can be written this way. And we know that center of mass is defined as where m is the total mass of the body. So, this can be written as d s square m times r c m d t square, and which can be reduced to m times which you often write as m times okay. So, this is the equation of motion. Now, on the other hand, if we look for the rotational motion of the body, then what happens? So, here in this case, the issue is little bit complicated. Now, let us consider this is a mass, this will not put here, delta m I. This frame we will write as E 1, E 2, E 3, this is a point O prime, this is point O, and this will write as E 1, E 2, E 3. Frame E 1, E 2, E 3, this we call as the inertial frame, in which we can write the equation of motion, we can apply Newton's law. Okay. And frame E 1, E 2, E 3, we call this as the body frame. And this is a rotating frame. So, it is a rotation direction we can show as, let us say this is the rotation direction omega. and also we assume that somewhere say V I is the velocity of this point, and also the radius vector of the origin of the body frame, this we write as R O, okay. And radius vector of this point. So, little bit change I will make here. Let us say this point is lying somewhere else. Let us say we have a point here which is delta m I. This is delta m I, okay. And velocity of this point is V I. And this we indicate as rho I. And if we join these points here, this vector will show as R I. So, we know that the angular momentum will indicate it by for this particular particle as delta H I, okay. And we are writing here in terms of delta H I because we have to integrate it over the whole body, finally sum it over the whole body and calculate the angular momentum of the system. Okay. So, this delta H I we can write as R I cross the linear momentum of this particle, which is delta m I times V I. Okay. So, this is the radius vector linear momentum. Now, if we differentiate this, okay. So, differentiating this, it gives me d r I by d t cross delta m V I and we know that this quantity d r I by d t is nothing but V I. Okay, this is the velocity of this particle. Okay. I am assuming here that you are well aware of the vectors, okay, because it is a matter of the 12th class, and already we have discussed a lot about the vectors and its various operations. Now, here in this part, so this is V I cross V I, this will be 0. So, this part gets reduced to 0. So, this quantity this equal to 0, and therefore, H I this gets reduced to R I cross and as we know this quantity already we have written, this is R I cross delta F I. So, what we get from this place, and this we write as delta m I, which is the Mi stands for the torque. You can use also some other notation, but this is okay. Sorry, this is here we will write this as here in this place. This quantity then we write as delta Mi. Okay, therefore, this if we take the summation over this all the particles, so as we know this summation operator and the differential operator can be exchanged. So, we can write this as, and this we can write as dH by dt, and on the left hand side here we can write this as m. So, what this gives me, m equal to dH by dt. But see here in this case what we have got, this is the angular momentum we have calculated about this point O prime. So, this is the angular momentum about O prime. Okay. This is not the angular momentum, this V we have written, and this O. Okay. So, the story does not end here, we have to extend it, because this is the, say if you have an aircraft or the satellite and you are sitting on the ground. So, the angular momentum, as you are aware of, most of the time you are calculating about this point O, which happens to be the center of mass. Here in this case we have taken it a general point O, and right now we have not chosen this as the center of mass. Okay. So, and this is the point where we are calculating the angular momentum. So, you can say that this is the absolute angular momentum of this particle, okay, because this we are calculating in the inertial frame about this point O prime. Okay. So, we need to extend this further to go to the point that we want to describe. Quite often it is very easy to describe the system angular momentum about any point in the body itself. So, we reduce it to that form and we see that what benefit we get out of that. Okay. So, this is the m that we have written. Finally, we have got it in this format, and this can be written as r o, which is the radius vector of this point, and plus rho I. So, this r I is summation of this vector and this vector. So, the green and the red one. So, r o plus rho I plus delta f I. Okay. On the right hand side, so this quantity will be equal to this quantity, okay, this dH by dt, which we are calculating about this point. So, we write about this point d by dt and the angular momentum of the whole system, which we have written as r I cross delta p, which is nothing but the linear momentum of the particle. So, delta m times V I. Initially, we differentiated this quantity and then we have changed the operator. So, look here in this place somewhere we have done that. Okay. So, if we sum over this one summation where we have shown. Okay, you can take this equation. So, here this is the part we are discussing about. So, if we sum it over this point, okay, so summation will go inside. So, you have d by dt, you can take it outside. So, this particular equation we are choosing and using here in this place. Now, the left hand side, this particular part will use this whole thing in our expansion. So, this we can write as, because R 0 it is not dependent on this summation, R 0 is a particular point in the body. So, what we have done that in this frame we have fixed the point here itself, and we have not considered this to be the center of mass, and the center of mass will evolve out of this during course of our discussion. Okay. So, we utilize this equation to formulate our whole problem. So, we stop here, this is our basic equation, and we will continue here in the next lecture. Okay. Thank you very much.